In this problem, we have an example of some simple harmonic motion, but there's a couple different elements that are models that are involved as well. So the situation is this: we have a platform with a spring attached to it on a solid ground here, and we have we have a known spring constant K. We have an object that's above the platform of mass m at a distance y. We know this was this distance here as well. In this problem, we want to calculate a couple different things. I'll list them here. We want to find number one, the velocity of the block right before it hits the platform. B, the period of this simple harmonic motion. So after it hits, it's going to oscillate back and forth on the platform. C, the distance the springs compress when the speed of the block is a maximum. So I'll say y when the speed is a max, which we have to find where that point is. D, the max compression of the spring, so y max. And E, the amplitude of the motion. So let's take a look at this step by step. So you have an object here that's going to be dropped from rest, a known distance y above it, and we want to find the velocity right before or right as it hits the platform. So there's a couple different models we can use. We can probably use the kinematics model or the energy model. So for part A here, the hint is we can use either the kinematics model with gravity being the acceleration, or the energy model, energy bucket model. Those two should do it for us. Now after it hits, and the problem states that the object is going to stick to the platform, we're going to have a oscillation or a simple harmonic motion, and we want to find the period. So you have to look back to the equation that is the period for a mass on a spring situation, and that should solve it for you because you know the mass and you know the spring constant. Then we get in a couple different questions here about maximum displacements and so forth. So the key point of this problem is to recall that there's a 0 point where the spring is uncompressed, and that there's an equilibrium point, or I'll call it the EQ point, or the reference point where the oscillations occur about. So after it hits, well, going back, when you put the mass, if you were to just set the mass on the spring, it would come to a point here, the EQ line, where it would reach equilibrium, where basically the force due to the weight and the force of the spring would be equal and opposite, and it would come to rest at this point. And we have to remember that all oscillations will be relative to this line, this reference line or EQ line. So any oscillation, I'm drawing an arbitrary one here, when the thing oscillates up and down, will be relative to that. So the key is to find this point here, YEQ, which the hint for that is using the force model. At any rate, for part C, the speed at the maximum, when the displacement when the speed is a maximum. So the speed is a maximum right here on the EQ line. It's going to come to stop here. Max speed occurs right here on the EQ line, stops, and occurs right here on the EQ line again. So basically we want to find the speed at this point. Using the energy bucket model, we can do that. We have to take into account potential energies and elastic potential energies and so forth. So we can use the energy bucket model for that. The maximum compression. So the maximum compression, what they're stating or asking is relative to 0, what this maximum compression is all the way down there. So that full distance from the 0 point all the way to the bottom there where it comes to rest. And then finally the amplitude of the motion. So the amplitude of the motion, again, if you look at the diagram, and this is why the diagram is really important to overlay it on the problem, is this distance right here. That's the amplitude of the motion. But again, everything hinges upon this EQ line because all oscillations occur relative to that line. So we can find that using the force model, and we can use energy models to analyze the changes in kinetic and potential energy. Remember, gravitational as well as elastic spring potential energy.